Ladies and gentlemen, last time we considered induction on strings, so-called structural induction. Let's recall the formula for the induction principle. Okay, if some property holds for the empty string and for every symbol from our alphabet, for each string, of course, this, let it be. And for each string for our alphabet, if P of S, if our property P holds for S, then it holds for X column S for the string resulting from S after adding X to it. So if these two are true, then every string satisfies our property. So this is for each unary predicate on over strings. So this was the induction principle for strings. Hopefully we had enough practice with that principle at our previous lecture and also at the seminar. And now let's take another step, namely, let's consider induction for natural numbers. Of course, it is more useful than induction on strings, but still it is very, very similar to it. By the way, this set or collection or whatever of natural numbers we denote by such a stylish letter n, and we think that we know quite well what natural numbers are. So natural numbers is a set that consists of 0, 1, 2, and so on. And now we want to give an induction principle for such set. Okay. The induction principle for n. In fact, in practice, they use more than one form of the induction principle for naturals. We shall consider three most popular forms thereof. Okay, the first form will be called MIP. IP, of course, is for induction principle, and M is just for mathematical. The mathematical induction principle. Of course, that doesn't mean that two other forms are not mathematical. No. But we just want to mark it somehow. Okay. For each unary predicate, let it be phi. Let's learn Greek letters. Phi. In an alternative script, it would be something like that, but we prefer this one, so phi. For every unary predicate phi over naturals, if phi holds for 0, and for every natural number, if phi holds for that number n, then it holds for n plus 1 if these two are true. Then for every natural number, generally I will omit this qualification that n belongs to naturals. All quantifiers in our discourse today will be over naturals. So let's erase it. So, in order to prove that every natural number satisfies some property phi, it is sufficient to prove that 0 satisfies that property, and also this property might be somehow inherited from n to n plus 1. So if n satisfies, then n plus 1 satisfies as well. Now, let's try to see some similarity between this principle and the principle for strings. Of course, it is quite clear. Let's mark the respective objects. So, the corresponding objects. Of course, the empty string corresponds to 0. And the operation of adding new symbol to a string satisfies to, corresponds to what? Corresponds to increment, to increasing our number by 1. That's quite interesting. By the way, here we have quite a choice of symbol which we can append to S. But here 1 is unique. There is only way to increase the number by 1. So there are some differences. In fact, this principle might be looked upon as more general than this one. How? In fact, we may identify natural numbers with strings of some special form. For example, you may think that 0 is just some code for the empty string. 1 is the code for string. So our idea is to fix some particular symbol. If we fix it, we may construct the following correspondence between strings and natural numbers. So it is possible to understand naturals just as strings of some special form. Then this principle would be, of course, just a corollary, a consequence of this one. But in fact, it is not necessary for us. But anyway, let's notice that the following interesting fact, that every natural number is either 0 or is of the form n plus 1 or some other natural number n. Is it clear? No. So you know other natural numbers which are not of the form n plus 1, nor they are 0. Not possible. So, of course, every natural number, let's write this down, every natural number is either 0 or there exists some natural number n such that m plus 1 equals n. By the way, this is similar to the following statement for strings. Every string is either empty or of the form x column s. In fact, natural numbers might be also defined inductively as the following way. 0 is a natural number by definition, and if n is a natural number, then given some undefined primitive operation of increment, if n is natural, then n plus 1 is natural as well. But let's don't talk too much about this. We'd better have an example of application of this principle. Let's do it. Now, of course, there are some trivial applications. If somebody is not familiar, was not familiar for this principle earlier, they may benefit from considering the most trivial statements, of course. Let's do it. Let's consider the following statement. 1 plus 2 plus 3 plus n equals, by the way, do you know the formula for such a sum? N multiplied by n plus 1 divided by 2. By the way, you can, for example, check it in some particular example. So 3 multiplied by 4 divided by 2, that is 6, and of course, that's 6. So it doesn't fail in this example, but of course, that's not enough to prove it. Okay. Let's try to prove it. For every natural number, but 0 is a natural number. What does this statement means for 0? In fact, the right-hand side is well defined for 0 and equals 0. But what about the left-hand side? What does it mean? The sum of all naturals from 1 to 0, where 0 must be somehow greater than 1. There is quite a natural way to interpret it. We may say that this is 0, but let's take another approach and say that this equation is relevant only for naturals from 1 on. So we say that if n is greater or equals than 1, then. So now our statement, let's call it lemma 1, our statement is now an implication. It's not an equality, but an implication, where this easy inequality forms the assumption and our original equation forms the consequence. Okay, let's prove it. This is our phi of n. This implication might be true or false, depending on n. Is it clear? So it is some property of n, some predicate, some statement about n, some statement whose truth depends on n. For one n it might be false. For another one, it might be true. So this is phi of n. Phi of n. Let's prove it by induction. By induction, they say by induction on n. How is it possible to do that? Of course, we need that for each n, this implication is true. In order to check it, we need these two statements. Phi of 0, it is known as the base case or the base step. The base step of induction, or simply the base step of induction, and this statement is known as the inductive step. Much like this case, where our terminology was the same. The inductive step. So the base step and the inductive step. And when proven that inductive step, this assumption is called the inductive hypothesis. Or it is shortened to IH. IH stands for the inductive hypothesis. Okay, first of all, I need to verify the inductive step, the base step, that is phi of 0. Okay, what is phi of 0? If we substitute 0 for n here, we obtain the following implication. If 0 is greater or equals than 1, then some sum equals 0. The sum of all integers from 0 to 1. You may write it down the following, from 1 to 0, that is. But whatever this could mean, we see that this statement is simply false. As it is false, our implication is of course true. As from falsity, it follows everything. Okay? And now, let's check the inductive step. What do I need? I need to prove that for every n, if phi of n, then phi of n plus 1. As usual, in order to prove an implication under a universal quantifier, I will consider some arbitrary n, assume that phi of n holds, and I'll try to infer phi of n plus 1. Okay? Let's do it. So assume that we have some natural number n fixed, and we have phi of n. And what is phi of n? Phi of n is the following implication. If then 1 plus 2 and so on plus n equals this polynomial. Okay. And what do I need? What to erase, what to erase. So, is this part visible? Okay. Thank you. Thanks to you it is. So what do I need? Going very, very slowly for the benefit of those who were not familiar with this induction thing previously. What do I need? I need to prove phi of n plus 1. That is what? It is the following statement. If n plus 1 is greater than 0, then 1 plus 2 and so on plus n plus 1 equals what? I have to substitute n plus 1 for n. It is n plus 1 multiplied by n plus 1 plus 1. That is n plus 2. All this, the entire product over 2. I want to prove this statement. That's an implication. But this assumption is always true. So there is not much sense in assuming that it is true. Excuse me, it should be 1. Okay. But anyway, this is always true. It's always true, so there is no point in assuming it explicitly. So that means that I need this one. Okay. I need it. How is it possible to do so? N plus n plus 1. So let's look at our inductive hypothesis. The most natural thing to do here is to replace this term, this sum, by n multiplied by n plus 1 divided by 2. But that's not always possible. We have a precondition here. N must be at least 1. But in general, n might be 0. So I have two cases. Formally, I have two cases. So my first case is when n equals 0. When n equals 0, then I can't apply this implication, for its assumption is false, and it is not necessary that its conclusion is true. So what if n equals 0? If n equals 0, I can explicitly consider this thing. It is has the following form: 0 plus 1 equals 0 plus 1, 0 plus 2 multiplied by 2. But is it true or not? Let's compute it. That's 1, and this is 1 multiplied by 2 over 2. That is 1. Okay. That's okay. It holds. Is it clear? In fact, most of such trivial steps are applied almost automatically by any experienced operator. But we want to go more slowly, so we explicate all these steps. The first case, n is greater or equal than 1. If it is not 0, then it is at least 1. So we are considering naturals. In this case, the inductive hypothesis is applicable. So, inductive hypothesis says that whenever n is greater or equal than 1, then this sum equals this term. So 1 plus 2 and so on plus n equals n multiplied by n plus 1 over 2. Ha! Given this, we may easily rewrite and transform our left-hand side. Our left-hand side so by our inductive hypothesis, it would be just n multiplied by n plus 1 over 2, which is equal to this sum, plus n plus 1. Then we see what? It is just n plus 1 multiplied by n plus 2 plus 1. That is n plus 1 multiplied by n plus 2 over 2. Which is the right-hand side required. Is it clear? So, what does it mean? That means that I've got phi of n plus 1. Assuming that n is some arbitrary natural number and phi of n holds, I've got phi of n plus 1. So I have proved that this implication always holds. The base case is true, and the inductive step has been already checked. So by my mathematical induction principle, M is for mathematical, not for my, by MIP, by the mathematical induction principle, that means that phi of n holds for every n. So this implication is always true, which was the thing we need. Is it clear? Any questions, please? Now, let's consider a more interesting example. A more interesting example. So, let's free more space. Okay, MIP says that for each unary property phi, if phi of 0 holds, and for each n from phi of n it follows phi of n plus 1, then phi holds for every nature. Probably you will agree that 1 equals 1 over 2 plus 1 over 3 plus 1 over 6, isn't it? Let's check it. This is just 1, 6, 2, 6, 3, 6. So overall, 6 parts, that is 1. So, now I have the following representation of unity. of 1, where A1, A2, and A3 are 3 distinct naturals, 3 pairwise distinct naturals. Is it clear what does it mean that they are pairwise distinct? As a usual wording in mathematics. That means that every 2 are distinct. A1, say, differs from A2, A1 differs from A3, and A2 differs from A3. No 2 of these are equal. So, but my question will be as follows. But is it possible to express 1 for example as a sum of 4 such numbers? How? So, please. Where, of course, they should be pairwise distinct. You can't just take 1/4 and repeat it 4 times. No. How is it possible? But in the spirit of induction, it would be nice to somehow use this equation in order to obtain these numbers. Let's think about it. This is a creativity moment. Not just some mechanical application of logic, but some creative thinking. So, how is it possible? Or maybe don't apply this one, but obtain the expression for 1 in some other way. Any ideas, ladies and gentlemen? So, please. Of all primes up to some prime. So I don't know, say 1/2, and here say 1/2, 3, 5, 7. I don't know. I need 4 summons. So, but this does not hold. It's not true. You may check it. Doesn't hold. Well, anyway, let's check it. It is 3, 5, 15, 15 plus 10 plus 6 plus 1. How many? 30. 30, and it is, this 32 greater than 1. Over 9 plus over 18. This one? Oh, let's check it. That's interesting. So here we have 9, 6, 2, 1. Oh, that's it. Yes. That's nice. So, but can you extend this idea? So that's true, is it? Let's check. I think it is so. Of course, okay, that's it. Why not? Okay, that's nice. But what if you want to obtain such an expression for 5 summons? Can you generalize the way you have obtained this representation from this one? Is it possible to generalize it? But maybe it is. Maybe it is. I just don't know. But there is a very easy way to obtain a general procedure that gives us one more summand. Assume that 1 equals this sum. But that means that 1 over 2 equals this sum. Of course, it's possible to divide both parts by 2. But that means that one will equal this sum, where, of course, 2 is not equal to any 2 multiplied by an. Why is it so? Because no a might be equal to 1. If our n is greater than 1, if we have more than one summand. Is it clear? So another way to obtain such an expression is to divide both sides by 2 and add 1/2 to them. So it is just 1 over 2 plus 1 over 4 plus 1 over 6 plus 1 over 12. Is it clear? You may check it. So here we have 6 over 12, 3, 6, 3, 2, 1, that's 12. Okay. And now let's formalize this idea using induction. By the way, is it possible to do this for one summand? Why not? Of course it is. But what about 2 summands? Do there exist 2 distinct numbers such that the sum of their inverses equals 1? Is it possible? If they are distinct, that means that one of these numbers is less than 1/2. Then the other one would be greater than 1/2. But such a number cannot be greater than 1/2 when it is when the respective a is not 1. But here, of course, our a's cannot be 1. Is it clear? So that's not possible. It's not true. For 2, it is not possible. So it's possible for 1. Of course, it is not possible for 0. Possible for 1. Not possible for 2. Possible for 3 and any subsequent number. So, of course, the case of 1 is somewhat peculiar, and we want to start from 3. So, I'll state our lemma the following way. For each n, if n is at least 3, then there exist numbers a1, an, such that 1 is the sum of the inverses, and these numbers are pairwise distinct. Are pairwise distinct. Is it clear? Okay, let's prove it. This implication is our phi of n. Of course, as usual, we start from 0. Sometimes in high school courses, they say that you may start your induction from any number you want. So you may change the base for some number, say change it to 3, and then here you will have that for each n greater than that number, greater or equal than 3. But in general mathematics, you don't want to change the principle. You don't want to change the axiom when you may easily change the parameter phi, namely taking an implication rather than just this statement. Okay. So, the base case is trivial. The base case is of the following form. If 0 is greater or equal than 3, then something. But anyway, that's false. So, our implication is true. That's okay and is not worth any further consideration. Is it clear? Now, let's check the inductive step. I will be more terse this time. So we have the following inductive hypothesis. If n is greater than 3, then there exists such numbers so that 1 equals the sum, and so on. So assume that we have our statement for n. And we need the same statement, the same implication, but for n plus 1. So there exists a1, an plus 1, so that. Is it clear? Okay. But essentially, our statement starts from 3. So all cases when n is less than 3, they are trivial, while the case for n being equal to 3 is, in fact, the basic one. Okay. First case. N is less than 3. If n is, excuse me, n plus 1 is less than 3, which is equivalent to n is what? Less than 2. That is 0 or 1. If n plus 1 is less than 3, then the statement that n plus 1 is greater or equal than 3, it is just false. If it is false, the implication is true, trivially. Is it clear? The second case. N plus 1 is exactly 3. By the way, then n is exactly 2. 2 is less than 3. So I can't apply my inductive hypothesis. Why? It is for n being at least 3. But now my n is 2. The inductive hypothesis is not applicable, but that's not that bad. The inductive hypothesis is not applicable. Yet, I may provide the numbers explicitly. You know, 1 equals this sum. So I may take 2 as A1, 3 as A2, and 6 as A3. Is it clear? Okay. In this case, our statement is true as well. I have, in fact, provided the numbers. Okay. And the third case. The third case is as follows. Now n plus 1 is greater than 3. But if n plus 1 is greater than 3, then n is at least 3. And now we may apply our inductive hypothesis. Now the inductive hypothesis is applicable. And gives us that there exist some numbers a1, an, so that 1 equals this sum, and the numbers are pairwise distinct. Are pairwise distinct. Okay. And now I know this thing. And then, of course, I see that 1 over 2 equals the sum whence 1 so I may take this as a1 prime, an prime, this is just an plus 1 prime. So I have provided the numbers. The only remaining issue is why these numbers are pairwise distinct. Okay. Assume that I differs from J. Then I know that AI's does not equal AJ. AI doesn't equal AJY because they are pairwise distinct by our inductive hypothesis. If these numbers are distinct, then still twice these numbers are distinct as well. But why this one? Every such number is distinct from 2. But what if some twice AI equals 2? Then, of course, AI equal 1. That means that in our sum we have this and that. That's not possible. It's not possible. That means that 1 is at least 1 plus 1/2, which is clearly not true. Is it clear? Any questions? So I have proved both that this holds for 0, and for every n, if it holds for n, it must hold for n plus 1 as well. Then my statement, my application is true for every natural number n. So for every natural number greater or equal than 0, I have such a representation of 1. Is it clear? No? Of course, that's not true. So we have a contradiction. We have assumed that at least one number is 2. So they are not pairwise distinct. So we have the following conclusion. So for each I, 2 multiplied by I does not equal 2. So this is a proof from the contrary. I have assumed that 2, we already have 2 somewhere here. So, but that's not possible. For otherwise, this absurd inequality would be true, while it is not, of course. Okay. Enough for our for this form of induction, and let's learn another very popular and very important form. This would be so-called the least number principle. What is it? Okay. Assume that some natural numbers are blue, whatever it could mean. We will also assume that, in fact, at least one number is blue. By the way, what do you think about the following statement? There is the least blue number, which is blue, but no lesser number is blue. By the way, do you know the least even number? And what about 0? 0 equals 0 plus 0, or 0 or twice 0, even. Do you know the least odd number? Odd means not even. 1. Do you know the least prime number? Do you know primes? So what is the least prime number? 2, of course. Do you know the least number which is divisible by 3 and by 5? 15, of course. So, for whatever property of naturals, when there is a number, at least one number, that enjoys such property, there is the least number with this property. And what if you take some contradictory property, which no natural number satisfies? Say, what is the least natural number which is divisible by 4 but not by 2? Divisible by 4 but not divisible by 2. Of course, that's not possible. No numbers divisible by 4 but not divisible by 2. In other words, every number which is divisible by 4 is divisible by 2 as well. Okay. So our idea is as follows. For any property, be it blueness or primeness or divisibility by 3 and by 5, if there is a number with that property, there is the least such number. So it is known, this principle is known as LNP, or the least number principle. Let's state it. For every unary property phi, unary, that means it takes one argument. For every unary property phi, if there is a natural number that satisfies phi, then there is some other number, say m, maybe some other, maybe the same, it doesn't matter. In general, then there is such a number, so that phi of m and for every k less than m, phi of k fails. So what does it mean? This is in symbols, but we may simplify it or rephrase using plain English. So this m is the least number with property phi. With property phi. Indeed, m satisfies phi and no number less than m, no number k less than m satisfies phi. Is it clear? Phi is true for m, but it is false, that is, not phi is true for every k which is less than m. Is it clear? It is a symbolical representation for the following phrase. M is the least number with property phi. Okay. Let's apply this principle. As usual, at first we will have a trivial application, then maybe more interesting. Lemma 3. For each natural number n is less than 2 to the power n. By the way, is it true or false? What do you think? 2 to the power 0 equals what? Of course. Which is, by the way, greater than 0. 2 to the power 1 equals, which is greater than 1. 2 to the power 2 equals 4, which is greater than 2, and so on. So probably it is true. That's our conjecture. Let's prove it using the least number principle. How is it possible to do so? The main idea is to argue from the contrary. Assume that it is not true, and then try to get a contradiction. Assume that's not true. What does it mean? What does it mean that not for every natural this inequality holds? That means what? Not for every. That means that they exist. There is, of course. Then there exists some n, so that n is not less than 2 to the power n. But what does it mean? What does it mean? Not less. No less in naturals means that it is greater or equal. Okay. And our next step would be the following one. Let's take the least number with such property. Let's take the least such n. Let m be the least number such that m is greater or equal than 2 to power m. And now we have the application of induction principle. By the way, why this one is a form of induction? Maybe it's not that clear. We shall prove that this principle is logically equivalent to the principle of mathematical induction. In particular, this very statement might be proved by induction. We shall establish this fact later, but first of all, let's have some practice. Let's obtain some intuition. By LNP, such m indeed exists. Oh. It is the least one. We know that every natural number is either 0 or some lesser number plus 1. Do you agree? So, let's consider the two cases. The first case, our m equals 0, but that's not possible. Then 0 is greater or equal than 1. Ha! That's not true. We have got a contradiction. And we want to get a contradiction. And now we have got what we want. The second case, m is k plus 1 for some k. But then k is less than m. Do you agree? You know, k is less than k plus 1. So k is less than m. But m was the least number with this strange property. As m was or is the least as it is the least number with such an equation, then for k it doesn't hold, then k is less than 2 to the power k. Is it clear? For k, this property, this negation, does not hold. That means that k is less than 2 to the power k. So we have that k is less than, while m, which is k plus 1, is greater or equal than 2 to power k plus 1. But what is it? It means that it is exactly 2 to the power k taken twice. So, but 2 to the power k is greater than k. That means that this right-hand side is greater than 2 multiplied by k. Is it clear? So I see that k plus 1 is greater than 2 multiplied by k. 2 multiplied by k, twice k is less than k plus 1. But what's possible? I can subtract k from both sides. Subtraction. If I subtract, then I'll obtain one copy of k here and what? 1 there. Okay. K is less than 1. K is less than 1. We are considering naturals. That means that k is 0. 0 is the only natural which is less than 1. but then m equals what? K plus 1, that is 1. But we know that for m, we have such a property. So we see that 1 is greater or equal than 2 to the power 1, which is false. We have got a contradiction. So what was the main idea? We want to prove that every number satisfies such inequality. For the contrary, assume that not every number satisfies. And then we shall try to get a contradiction. If not every satisfies, then there is a number which does not satisfy. Then we may take the least such a number. And then we are considering two cases. Either this number is 0 or it is something plus 1. But that something is less than our number. Hence, for this less number, we have a useful assumption, namely that it doesn't satisfy this negated statement, which means that this number is less than 2 to power k. And combining these two assumptions, we have obtained a contradiction. Is it clear? So, this was the least number principle. Of course, it's much more interesting to apply this principle in a more complicated, more demanding situation, such that, for example, the following one. This principle is especially popular in so-called number theory, in theory of integer numbers. You have a dedicated course for numbers, as I know. So, in that course, in many cases, you will benefit from the least number principle. It's very popular and widely used. For example, we may even prove something as an example from number theory. But anyway, now we have not much time. And first, let's state the problem which you most likely will solve at your seminar tomorrow, or maybe some other day. So the problem is as follows. Let's consider the following equation. 8 multiplied by a to the power 4, 4 multiplied by b to the power 4, twice c to the power 4, d to the power 4 equals what? A, b, c, d? Oh, okay. Let's consider the following equation. Does it have any solutions in integer numbers? You see, we are talking about integers, not naturals, but somehow we may reduce this problem to a problem about naturals and then apply induction in some form. So, does it have any integer solution? Is it clear what an integer solution is? An integer solution is a tuple an ordered array or sequence or tuple of integer numbers such that they satisfy this equation. So, dear students, any integer solution, one solution is obvious. Of course. Of course. Let's take 0, 0, 0. This tuple satisfies our equation. But more complicated question. What about any other solutions? What do you think about it? Is there any other one? Either there is or there isn't. But if there is a solution, probably you might provide it, give it, or show it. And there is, if there is no solution, there should be a way to prove it, to prove that there is no solution. First of all, and in fact the last thing we shall do today is the following observation. Let's make the following observation. First of all, assume that there is a solution. This is a natural procedure, in fact. If you want to prove that some object does not exist, assume that it does, and infer that its properties are contradictive. That this object should be, say, I don't know, both odd and even number, which is not possible. So assume that say x, y, z, w is an integer solution. First of all, here we have even exponentials, so they ignore the sign. If x, y, z, w is a solution, then the tuple of the absolute values is a solution as well. Is it clear? You know that for the fourth power, 8 to the power 4 equals, x to the power 4 equals minus x to the power 4. So it makes no difference whether they are positive or negative. So we may assume that they are not negative. So without loss of generality, have you seen previously this abbreviation? It's very common in mathematics. Without loss of generality. That means that if you assume it, you won't lose anything. So this assumption costs nothing. Of course, there might be solutions with negative numbers, but if there is a solution with negative numbers, there is a solution with all numbers non-negative, as we have already proved. So without loss of generality, we may think that this, all these four numbers are natural. Okay. are natural, that is, they are greater or equal than 0. And now, okay. It won't take much time. Just a minute. What can you say about this integer number in terms of divisibility? Here we have 8 multiplied by something plus 4 multiplied by something plus 2 multiplied by something. What can you say about it? Which one? Why 2? It's not 2, but it is. It's divisible by 2. That number is even. Why? No, as you can say, express it in the following way. So it's divisible by 2, it is twice something. Twice some integer, so that's even. But w equals this number, w to the 4th power. Hence, this one is even as well. Even means divisible by 2. By the way, have you had such a symbol? 2 divides x. So, we know that 2 divides the 4th power of w. What does it mean? According to our knowledge of arithmetic, is it possible that 2 does not divide w? No, that means that w is divisible by 2, is even. That means that there exists some w prime, so that w equals twice w prime. Such an integer number, that is, of course. But if I substitute it here, I'll obtain 16 to w prime to the 4th power. Is it clear? But then I can do what? Divide both sides by 2. And then I can look at z. Yeah, I see that some even number plus z equals even. So z is the difference of 2 even numbers. That means that z is even as well. And so on. Similarly, I may prove that x, y, and z and w are all even. Then I'll substitute such expressions for these numbers to the original equation, cancel 16 out, divide both sides by 16, that is 2 to the power 4, and then I'll obtain the same equation, but for the halves of x, y, z, and w. So I'll see that every our number is and gets twice less. So given one natural solution, I'll take a solution which is twice less. And the same would be true for that solution. So that means that it is possible to indefinitely divide our solution by 2. But if this solution is consists of natural numbers, non-zero natural numbers, it's not possible. No natural number might be divided by 2 indefinitely. Staying natural, that is. So that is the main idea. You may think about it in advance. And finally, I hope you will have this problem solved in seminar. How about the question? How about x, y, z, and w being equal to 0? Of course, of course. We have noticed that 4 zeros is a solution. But is there any other solution? Non-zero solutions? Of course. Of course. We are interested in non-zero solution. 4 zeros is a solution. Okay, thank you. Any more questions? So please. By the way, if you have a question later, not during our lecture, you may use our Telegram group.